This is a demonstration of the Inometrix Virtual Reference Analyzer. In this experiment, we're testing a fiber, okay, a short-length patch cord cable, in which we connect using configuration B from the manual. So we've got an APC or FC APC connector to FC APC connector between the device under test, which is a fiber patch cord cable, and the DUT port. So the reason why we connect this FC APC to FC APC is to keep the FC APC connector on the DUT port clean, because we can very easily clean the facet of this connector. Now, to clean our connectors, we recommend using commercially available fiber cleaners, or even the Kim wipes with isopropyl alcohol. So it's very important to keep our facets clean because we're using them as reflection points. Okay. Now, if you're not using connectorized components, what we recommend using is a proper cleaver. Okay, because we need to make sure that the facets are 90 degrees to the fiber. So recommend using these, and what you'd be using them with is probably an adapter, so a bare fiber adapter. We use the bullet bare fiber adapters as they're quite good. So I would recommend using these. Now for this experiment, we have the FC PC connectors on both ends of the device under test, because we're creating a Fabry-Perot cavity on both sides of this device under test. Now, if the device under test had an APC side, we'd simply replace this connector, the APC to APC connector, with an APC to PC, or an FC APC to an FC PC connector, so that we have the reflection point at the junction between this intermediary device. So to start the experiment, and we will, at the end of the video, we do have the screenshot. We will be, I know you can't see very well the screenshot in the video, but we will provide the screenshot of this experiment. So let's start the experiment. So we've got everything connected according to the manual, and we're using configuration B in the manual for a fiber patch cord cable, or any device where we have a Fabry-Perot cavity. So so we're going to set our start wavelength at 1510, and our stop wavelength at 1640. Our output power is 3 dB. Now, to ensure that the virtual reference analyzer is connected to the tunable laser via GPIB and everything, and they're communicating with each other, simply click on this arrow here. If you click and refresh it, and when you click it again, you'll get the GPIB, whatever port your laser is on. You should get one of them, and just click on the auto-detected port. Now, since in this experiment we're using an 81640A mainframe, we're using an 81642A tunable laser. So we're going to select the Agilent 8164A mainframe. By default, the number of points is 50. We can change that. We're not going to be compressing the interference pattern. We'll demonstrate that in a later experiment. And we're not using a bulk reflective element. And for example, a bulk reflective element would be a fiber bright grating, which we'll show in a later video. So let's start the experiment. So we start the scan. We click on the scan button, and you hear a click when the tunable laser starts. Okay, the tunable laser is scanning. It depends on your sweep speed. We have set the sweep speed to 10 nanometers per second with the laser, because we found that gives us the best results. Ensure that your coherence control is off on the laser. That's actually a very important thing to keep in mind. Make sure that the coherence control stays off, because we need to ensure that the front and back facets of the tunable laser are reflecting. We need to ensure that there is a reflection. So the laser has scanned, and now we're going to be importing the data. You'll see that on the raw scan pattern. So as soon as that happens, you see that there's a raw scan pattern that comes up on the display. And the next step is, if we want to use the full bandwidth, we're not going to play with these dials at the bottom. We could use them to reduce the bandwidth that's needed. So if we press OK, we move on to the balancing part. Now, this balancing is optional. It typically it will auto balance. So what's involved here? What's going on behind the scenes? So you see the power spectrum. So what that is the power spectrum for the interference pattern, and it's looking for a specific frequency. And what is that frequency? Well, the device under test produces a Fabry-Perot cavity, or there is a Fabry-Perot cavity around the device under test, and that produces an interference pattern with an associated frequency. And that frequency gives you the group delay of this device under test. So the device under test has a specific group delay. The virtual reference analyzer creates a virtual reference that is a free space analog, or it's a free space Fabry-Perot cavity, or even a free space unbalanced Michelson, because the interference pattern will be the same, even for a Mach-Zehnder. So it creates an unbalanced interferometer, and just for simplicity, let's call it a Fabry-Perot, and it's free space. So what's happening here is that we take that raw scan pattern, okay, and we balance it. Okay, so we have a cavity, and we're balancing the cavity with a free space cavity. And what that does is that creates a second order interference pattern. And the second order interference pattern is seen in the manual balance. And you can manually balance your interferometer. So what are we doing when we manually balance? Well, we're increasing the group delay or decreasing the group delay of our virtual reference. Okay, it's the same thing that you would be doing with a Michelson. So you're increasing your reference path length or decreasing your reference path length. And this is used to plot the dispersion diagram, or the dispersion plot. Okay, so what we have here is we have an interference pattern with an envelope that looks exactly the same as what the first order interference pattern of a Michelson or a Mach-Zehnder type interference pattern would look like at the balance point. Now I must stress, this is spectral interferometry, so there is a characteristic interference pattern we're looking at, and it's a large period in the center and gradually decreasing period towards away from that central wavelength. And that central wavelength, where the large, for lack of a better word, valley or peak occurs, is where the group delays are balanced. That's where the group delay in both arms, the real part, which is the device under test, and the virtual part. It's where they are in balance. It's where they're equal. And this is the same thing that would happen in a Michelson. So let's continue with the experiment. We've got to our balance point here. And you can play with the number of points, and that basically increases your resolution of your spectrum. And this power spectrum, it gets us an estimate of where, how long the group delay of the fiber under test is. Now, it's not going to be perfect, so that's where you can actually manually balance. It's optional because it's done automatically later on, but you can actually manually balance your interferometer using this. Now, the sensitivity just basically increases. If you increase the sensitivity, you increase the amount of your step every time you change your virtual reference length. Okay, so since we're at balance, and I know you can't see very well on the screen, so we will provide a screenshot of what's happening here. We're going to press OK to advance to the fitting part of our screen. So on the fitting tab, we have the virtual reference pattern, and we have a fit to that pattern. And the key here is we want to have a single point for every peak or valley in the interference pattern. Okay? Only one point we want to have. And we don't want to have too many points because then it could throw off our calculation of the center wavelength of the interference pattern, that point where the group delay matches. So we're producing a plot. We're going to be producing a plot. Now, if this was a standard Michelson or Mach-Zehnder, we'd have to rescan for every single interference pattern that we want to produce. But because we're using this virtual reference, we have a real scan, and we're just basically changing our virtual reference after with post-processing. So that drastically reduces the amount of time spent on this measurement. So as you can see here, we have the results of the interference pattern, or of the measurement. We see that the group delay is increasing as a function of wavelength, as expected with SMF. And we can, if you look at the bottom of the results tab, you have the group delay, you have group velocity dispersion, and you have the dispersion length. This is the total dispersion observed by a device. So now I'm going to just show you a little bit more features. Now, since the only part of our experiment is that's real that we need to save is the scan itself, because that's the raw interference pattern, the raw Fabry-Perot interference pattern. The rest, with the software, we can just redo the experiment for more points if we so choose, or less points if that's what we want. So if we click Save Scan, it brings up a screen where we can save the raw scan data. It's about a 19 megabytes, 19 to 27 megabyte file, depending on your bandwidth. So I'm going to save. I'm going to pull up my keyboard, and I'm going to save. I'm going to save the. I'm going to save this as a scan of SMF 28, let's say. Okay. So I'm going to push enter, and the file will be saved. It's saved as just a file with no name. So you can open it in Notepad, or you can open it in Excel. It doesn't have a file extension associated with it, so you can bring it into any. You can bring it into MATLAB or whatever program you want. So that's saved. I've saved that to the desktop here. The other feature, if I'm happy with the results that have been obtained, I can actually export the results from the scan, and it's going to export it to, again, a similar file with no extension. You can actually change the extension if you're using Windows to .text, and you can open it up in Notepad or whatever you like. Excel would work as well. So I'm going to do that right now. I'm going to export the results, and I'm going to say results. Results of SMF 28 scan, and then push enter. So I've now saved the results to just it could be a text file if you want to do that. So that's the end of this section where we've tested a single mode fiber using virtual reference interferometry.